Okay, example 6, find y prime if x over x plus y equals 2x squared plus 3. Now, looking at this problem in its current structure, I've got x over x plus y, which is a quotient which requires the use of the quotient rule. We have 2x squared, which is just a single 2x squared, so it's just 4x, that's its derivative. We got 3, which is just a number, its derivative is 0, so that right side's really easy. Left side, though, is the quotient rule, which isn't the hardest thing in the world to do. But within implicit differentiation, it sometimes gets a little confusing about where things go and where dy dx is going, how to handle that. There's an option for this problem and problems of this variety, if you wish. If I put this entire side over 1, that makes a fraction look. If I cross multiply these two fractions, I'm going to create an equivalent equation that uses also probably implicit differentiation to solve, but it won't require the quotient rule. So some people dislike the quotient rule. Some people forget the quotient rule. When it comes time to take a test or a quiz, it's something like low, D, high, and there's some rhyming and stuff. I can't remember. So, you know, if you can't remember the quotient rule, this is a way of getting around it. If I cross multiply this product, x times 1, equals this product. Now notice it's binomial times binomial, so we have to FOIL it. 2x squared times x makes 2x cubed. That's first times first. Outside times outside, x times 3 makes plus 3x. Inside times inside makes plus 2x squared y. And last times last makes plus 3y. The equation I have written there is equivalent to the original problem. And if I do an assessment of the two equations as far as which one's easier to differentiate. So again, the top one, the right-hand side, was very basic. 4x plus 3, done. The left side is a quotient rule, a little bit complicated. The bottom equation, we have x, we have 2x cubed, we have 3x, we have 3y. Those are all just basic equations, right? Power rule, power rule, power rule, power rule. Then we have 2x squared y, which is the product rule, in a pretty simple form. To me, that bottom equation looks a lot simpler, so I would probably go with that one. But again, keep that in mind. You have options. You don't have to do calculus immediately. You can do some algebra first to make the problem into an easier structure, maybe. One other thing I noticed as I was doing all this comparison was 3x and x are like terms. So if I wanted to combine some like terms, let's say move the x over here, I end up with 0 equals 2x cubed plus 2x plus 2x squared y plus 3y. That's also equivalent. So now I'm ready to differentiate. Okay, for me, that blue equation at the bottom is what I'd be differentiating because I put some thought into it before I started differentiating. Okay, again, step one of every calculus problem at this point should be think. Okay, consider options, consider structures, think about stuff, what differentiation rules should you use. Be doing that on homework so that in a test, that thinking takes much less time and it allows you to very quickly get to a good decision. I'm going to shrink that up. I grouped in all the highlights. There we go. That's better. And then do that. All right. So again, as far as differentiation, this is the only one that requires me a lot of thought. The rest of them are pretty basic, right? And this is a product rule. This is going to be function 1 in green and function 2 in red. That's how I'm going to decide to do it. As long as you get the x and the y separated, it doesn't matter what function 1 and function 2 are. If I want to put the 2 with the y, I could. But the fact that they're separated by that x squared, I'd rather just keep the 2 and the x squared together. So the derivative of 0 is 0. The derivative of 2x cubed is 6x squared. Nothing extra necessary because it's x. Derivative of 2x is 2. Also nothing extra necessary because it's a function of x. Plus, now I'm going to do the product rule. And again, product rule is 1d2 plus 2d1. Again, function 1 I've got in green, function 2 I've got in red. When I differentiate, that's when I have to worry about the dy dx, the decision whether or not I got to put that on. So when I write down function 1, 2x squared, I just write it down. d2, the derivative of y is 1, and I'm differentiating y, so I've got to put a dy dx on it. product rule always has a plus sign in the middle. And then 2, when I write down function 2, I don't care about anything, I just write it down. Function 2 is y. Then I differentiate 1, derivative of 2x squared is 4x. And that's an x expression, nothing extra necessary. And then finally, the derivative of 3y is 3, and that is a y expression, so I got to put a dy dx on its derivative. So again, everything in blue on that board is a derivative. So every one of those blue things I had to establish, is it x or is it y, to establish this dy dx. X doesn't have dy dx. X doesn't have dy dx. 3y does have dy dx. What's in red here is a derivative. I'm differentiating y, I put a dy dx. What's in green is a derivative. I'm differentiating 2x squared. I'm not putting dy dx. So again, that's how you make that decision. It's not just some random thing. I want to put it there because I feel like it. Okay. Haven't seen a dy dx in a while, so let's write one down real quick so it makes it look like my paper looks like what it looks like on the board in class. But there's a reason why dy dx is showing up. I'm differentiating something involving y. I put it. Alright, at this point, these two guys contain dy dx, the rest don't. The easiest fix, I would say, would be to move this guy and this guy over to the left, leaving everything else to the right. Now let me show you one corner cutting step you can do. Okay, I always move that stuff over to one side, separating the two things, right? The stuff I move over on that side always has dy dx attached to it, right? Alright, so if I assume that established idea, that everything coming over here is going to have a dy dx attached to it. The very next step, I'm supposed to factor that dy dx out. I can go ahead and make a group dy dx term, and as I move stuff over, just not write the dy dx inside the parentheses. So this term here is a positive 2x squared altogether, right? Positive 2x squared is what that is. So negative 2x squared dy dx, and this is a positive 3 dy dx, so minus 3 goes to the other side, and then move it to the other side, change the sign, the dy dx. So if you want to go ahead and pull that dy dx out as you move things over, if you're comfortable doing that, that's fine. If you're more comfortable getting everything over first and taking the dy dx out second, that's fine also, take your pick. I personally do that in my work. It saves me a step. Okay. What's left on the right hand side, what didn't move was 6x squared plus 2 and plus 4xy. So all those things stay on the right-hand side. Right-hand side is pretty boring. Left-hand side is where all the action's happening, right? Moved everything over there, took the dy dx out. And the final step, again, I've got something times what I want equals something else. I've got to divide by the something being multiplied. So I'm dividing by 2x squared plus 3, or negative 2x squared minus 3. So those cancel. Dy dx equals is left. And there's your answer. There's 3 terms on top, 2 terms on the bottom. Okay, that's the correct answer. Notice that every term is even except for 3. If this said negative 2x squared minus 6, now I could reduce by 2. Alright? But the fact that even, not even, you can't divide by 2. These 3 have x's, those 2 don't. So reduction is not possible in this one. Very, very seldom is. Occasionally it happens. I'm not that concerned about reducing a fraction by 2. Okay. If you reduce by 37, that's great. Makes numbers a lot smaller, but divided by 2 doesn't make things much smaller. So honestly, I would stop right there. And again, if you didn't make that decision that I made immediately that, hey, I can cross multiply this thing to get down to this simpler structure, you would have gotten the same answer. It would have looked differently though. You would have had some complex fractions in your work and it would have been kind of ugly to deal with. At some point, I think some cross multiplication is necessary anyway. So look for a possibility whenever the quotient rule shows up in a problem. Is there some way to cross multiply or get the thing out of there? Or if it's like this big function with fractions in it, multiplying by a common denominator to get rid of those fractions is legal. You can do that. And it can get you down to just a level where product rule is happening. In my opinion, product rule is a lot easier with implicit differentiation than the quotient rule is. I think at times it's unavoidable, but if you can make it happen, it's worth doing.